So our next session, there are 9 finalists here for the Hackaday Prize. We had 2 tracks this year for the Hackaday Prize. One of them was the best product track. And there are 7 of 10 finalists here for that. And there are 2 for the regular track Hackaday Prize finalists here for that. So the next 7 talks are finalists. So with that, I will ask Zach Fredin. Close enough, right? He learned to solder when he was 6 years old from Heathkit videos, and when he was 9, he was making neon sign transformers.
Ninth grade.
Ninth grade.
9 years old for 6,000 volts. That's pushing it.
Yeah, that's a little pushing it.
All right. I apologize for the title. It got a little lengthy. Intended to change it at some point. Perfect. There you go. Thank you, Chris.
Welcome.
All right. There we go. Same title. So I'm not an electrical engineer. I did a project that focuses on neuroscience. I'm also not a neuroscientist. So my goal here is to convince you that anybody that has the inkling to do so can take a project, take it through pilot-scale production, which I'll kind of define in a second. And you should do it right now. We're at a better point now than we were 10 years ago. It's way more possible for anyone that wants to do this stuff in their basement. So we'll talk about what I consider pilot-scale production. Again, not being an electrical engineer, so I'm sure there's other definitions out there. We're going to use the only electronics project I've ever done as the case study. So hopefully we can kind of teach by example a little bit. I'll give you guys some hard numbers, especially related to cost and so forth. Then we'll talk about why there's a bit of a sense of urgency about this. Again, why it's important that we think about doing this now. So pilot-scale production. Well, let's see if the GIF image works. Yeah, 90s technology right there. Very nice. So pilot-scale production doesn't mean 5 units on a breadboard. It doesn't mean a shipping container full of your project. It's kind of in that awkward area where you want to make enough devices to send out to the world, but you're not ready to actually scale up production. So I'm going to say it's about 100 widgets. That's how I defined it myself, was 100 devices. Why do you want to do that? Well, this is a San Diego Maker Faire a couple weeks ago. We were teaching a bunch of young future neuroscientists about neuroscience. We needed enough devices that we could give them to kids to play with and not worry if one of them broke. So if you're developing a hardware project and you make 5 things, you're going to treat them very nicely. But if you make 100 of them, chances are you can actually do some stress testing on them. These are the first 4 that I made. So if I had made 5 of these devices, I would have a 20% yield. You can see this one looks great. It's because the chip is on backwards. All right. This one looks bad because the chip is on forwards because I desoldered it and reattached it. That never worked. This one, I got a little aggressive with the solder paste. This one it's an RGB LED. It only showed up green, so something went wrong. But again, if I hadn't made 100 boards, I would be out of luck. I would have 1 device to show people. We'll talk about what the product is in a second too, and you'll understand why it's important to have a lot of them. And then the other point, we're not stuck with $10 non-temperature controlled Radio Shack soldering irons anymore. We don't need to deal with ferric chloride, staining our mom's basement sink. We have the tools, Osh Park and the rest of the PCB manufacturers out there that really make it possible to scale on your own. So I'm going to talk about my project a little bit. Again, I want to kind of use this as a case study, so hopefully you can pull some data points out of it. NeuroBites. Neuroscience is important. We believe that neuroscience is one of those frontiers in science that we still have a long ways to go with. There's serious diseases that affect a large amount of the world's population that we don't really understand. We have a basic concept of how they affect people, but we don't know how to cure them. Alzheimer's, Parkinson's, so forth. So this project is about teaching people about neuroscience, getting them interested in neuroscience, hopefully inspiring the next generation of young and eventually older neuroscientists. And a quick history on how it all started. I have a good friend who is an architect, so he likes to play around with Google Sketchup. He also dabbles in programming, so he likes to play with Ruby, and he got really interested reading a Wikipedia article about neurons and wanted to mash all those together. So he wrote a plugin for SketchUp that turns blocks of building into neurons. So you can actually create a biological neural network in Sketchup and then send signals through it and watch how they propagate through the network that you created. So in this case, green blocks are neurons that are at rest, and then as they receive signals, they turn red and they fire. And then that's a more complicated network. It's not animated, but if it was, you'd be able to see waves of information propagating through the network. It's my friend Andrew Salveson. He thought it was a fascinating concept. He wanted to commit it to hardware. We had brunch. I wanted a hardware project. We decided to partner up on this one. So we made a few iterations of prototypes. Version 0.2, you saw the video of before. There were 5 devices with NeoPixels and Arduinos on a breadboard. The next version had 9 devices and different indication and a little bit more less hastily written code. But ultimately, we wanted to make enough neurons that you could connect them in such a way that you wouldn't be able to predict what they did. We wanted to have a desk full of devices that you could freely connect and see what they do. So we used the Atmel ATtiny44 processor, a bunch of TE connectivity, the cheapest connectors I could find essentially, and some RGB LEDs for indication, KiCad, very basic circuit design, microprocessor, input connectors, and an LED and an output connector. Rolled up the board and sent it off to be fabricated. Then solder paste application. If you ever do solder paste at home, buy the Stencil. It's not worth using a toothpick for 100 different boards. Modified toaster oven, so it's got a temperature sensor in there, and it just kind of follows a reflow profile. There's a lot of these on Hackaday.io, so check them out if you want to do reflow at home. Then placing chips, relying on the solder mask to do the dirty work and fix all these bridges. Here's an image of the actual boards being reflowed. And then here they are being programmed. So pretty straightforward. So what are NeuroBytes? What are neurons? I don't want to get too into neuroscience as a subject. I'm not a neuroscientist myself, again. But essentially, they're little threshold detectors. So they have inputs on one side known as dendrites. Those are looking at information that's coming in, and then they're sending pulses down through their axon terminals to downstream neurons that are connected. So essentially, when this device or this cell receives enough inputs, it will fire, generate an action potential, send that signal downstream to downstream devices. This is the actual model once it's all assembled. So it's flipped 180 degrees, but you can see there's inputs on one side. There's a processor in the middle, and then there's an output that you can connect to other devices. So what can we do with this? Well, the classic demonstration is the patellar reflex, which is the one where you go to your doctor's office and they smack your knee with the hammer and it causes your knee to kick up. And we can simulate that. So again, the GIF image is not great, unfortunately, but you can see we're hitting a sensory element. It's a little snap action switch. That's sending a signal to this sensory NeuroBytes module, which is then sending a signal back through to the quadriceps muscle, aka a 9-gram servo motor. We later 3D printed that, so we have a little 3D printed model of a leg bone, and that was the reaction that I wanted. So I'm glad that everybody was like, "Oh, that's pretty cool," because we think that this kind of a visual learning for people that are at their, just starting to learn about neuroscience, we think it could be a really valuable tool for them. So those are NeuroBytes. You can also do other kind of creative things. So this is a little buggy that I built out of a cell phone box. Look this up offline, and I can walk you through the diagram of how the neural circuit works. But essentially, it just sends a series of pulses out to these continuous rotation servos, and then looks for inputs on its bump switches. And when it sees those, it'll reverse and go a different direction. Let's see if the animation works. Yeah, so there it is in my living room, avoiding my boot, and then avoiding this flower pot. And you can see when it hits, it'll actually flash. You'll see the action potentials come through. This is actually the 5th generation, the new prototype. So we're changing around. I don't know if anybody can see that. Come by afterwards if you want to take a closer look. But we're changing how indication happens, trying to clarify the display a little bit. This is the most important part. This is why we should do this thing now. So that's me in 7th grade. That was when I was at my peak of my electronics career. It kind of all went downhill from there, unfortunately. And this was in 9th grade when I got that aforementioned neon sign transformer. I learned that my driveway conducts electricity, and my parents started to get really concerned. But the point is, I didn't go to school for electrical engineering. I did other stuff, and I haven't been in electrical engineering for over a decade. But at this point, it's all out there. This is an example of projects that are designed to fit in a 1 square inch circuit board. It's on Hackaday. There's like 50 entrants right now. It's just kind of an ad hoc contest that someone put together. So if you're looking for inspiration, it's out there. There's people that are doing this. There's tools out there thank you. There's tools out there that are free. This is the programming platform. It's just a command line tool that we use to program the microprocessors. It's free. His name's AVR Dude. He thanks you. That's amazing. KiCad, incredible tool. Developed by CERN. Chris Gamble basically taught me everything I know about it. So thank you, Chris. He's going like this backstage. But yeah, 20 years ago, you weren't able to get free open source CAD tools. You had to go buy the programmer. Now you can make your own programmer out of your Arduino board. Very easy. The tools are cheap. I bought an old Lenovo laptop for $250 on eBay. Spend the money on a good soldering station, please. It'll save a lot of heartache in the long run. Buy some extra tools, and then let's see if this all works. Yeah. So that's actually the cost breakdown of the project. We made 125 of them for about $600. And that's processor, the LED, getting the circuit boards made, buying the connectors, buying all the passive components, buying the wire that wires them all together, and actually counting overage too. So when you buy a bunch of capacitors, you have to buy like the whole reel of them. So we factored that in as an overage expense. And to make 125 of them in my basement, they were still $479 a piece. Like that's low enough cost that if I'm going to spend a year working on a project, I'm willing to commit that sort of money, to a circuit board. I like this animation actually. It's one of my favorite ones. There's 4 neurons that are kind of connected in a loop here. You can't really see them that well, but they'll continuously drive pulses into this network, and it kind of does crazy, unpredictable things. So that was a fun one to put together. This is the last point. So you take a product, you take a design, you open source it, you share it. I shared mine on Hackaday.io. This is something that happened about a year ago. I got this email from a guy named Joe Berto. He's a biology professor, and he studied neuroscience. He's a neuroscientist, and he said this was a good idea. I'm not a neuroscientist, but he looked at this and he said, we could actually make this into a teaching tool. We could actually do a collaboration. And I flew out to Boston about 9 months ago, and we drew a big Venn diagram on the board, and there was this little sliver of intersection that was like NeuroBites, and over here it was Zach trying to figure out how to design circuits, and Joe is like a 10-year veteran of neuroscience education. So yeah, collaborators will come from any place, but you're not going to find them unless you share stuff, and it's a lot harder to share stuff if you don't actually share it. So I'll definitely plug the open source thing too. Yeah, and then we mashed it all together and made a company, NeuroTinker. That's us. Image credits, if you're interested, they're all from Wikipedia, but I figure that's a good thing to include. And that's all I have. Thank you. This little guy has, I coded this up on the airplane and got a lot of really weird looks. But I made a little binary counter on it that I thought was kind of cool. So if anyone wants to learn binary, come over this way.
That was awesome, Zach. If anyone has questions for Zach, he's going to be over there in the Q&A area in the hallway.